back before we went to break. And if you check your notes from before then, actually everyone should pull out their previous notes, pull out graph paper. I won't do like I did with my 7th graders and make you show me again that, excuse me, you have graph paper out and you're ready to go. But yeah, remember we're back at school. It's time to roll. So if we look at our notes from last time though, they probably say something like similarity and congruence. Who can tell me what we were doing and how we were setting up these ratios? Because I don't have the picture here to remember. Anybody? Bueller? I'm curious if you guys even know what movie I'm talking about. Okay, well, Elle, since you know what movie I'm talking about, can you remind us what we were doing to get to this work? How can we set up this ratio? Like, what were we doing that allowed us to set up this crazy ratio? Yeah, using the corresponding sides of similar triangles. So if we want to like have that one statement to kind of remind us of what we were doing back before break, we were using corresponding sides to create these similarity statements. And the biggest thing is order matters. So you should have this written in your notes somewhere, and this can maybe be a reference point for then coming back to what we were doing. So why triangles? We can break up any larger polygon into triangles. I spoke really quickly about the unit circle and how we're going to end up talking about that. And we should have had these. So I'm trying to get my keyboard out of the way, except I'm breaking things in the process. We should have had these rules written down, right? And one rule that we're not allowed to use. So this is all the stuff that we're going to use today. So this is why I was trying to bring us back and remind us. So put your eyes on this really quickly. Remember, we have angle-angle similarity, because if we know two angles, we really know all three. Angle-side-angle works as long as the side is included between the two corresponding angles. Angle-angle side as long as we're in the right order. Angle-side-side does not work. Side-angle side does work as long as the angle is included between those corresponding sides. Any questions? Alina?
Okay, so for the angle, side angle, and angle, angle, side, isn't it just the same thing as angle, angle, because you already know two angles?
Yeah.
Okay.
So when we get to triangle proofs, which is our next section, when we build proofs, you will like having the flexibility of using those things. And the other thing that angle side angle or angle angle side can tell us that angle angle doesn't tell us is what? Why do we have these? Why are these necessary sometimes when angle angle wouldn't be enough? Ooh, now you asked yourself into a corner, right? You asked the question that got yourself trapped. Because we're talking about triangle similarity and congruence. Does congruent angles tell us congruent triangles? No. Tells us similar triangles, right? So this angle angle only works for similarity. Whereas these two, when we involve a side, can work for congruence as well. So right now we're just focusing on similarity, but it's because the congruence gets related to it. So we should have a new page of notes. Everybody put a header on your notes. And what we're starting off with is triangle similarity ratios, right? And actually what we said before break is we're going to start setting up some funky ratios. So you can really head your paper with whatever you want. I'm going to say triangle similarity ratios. And today's date, we have escaped 2020. So 1/5/21. All right, warm-up problem. What is the ratio? Sorry, not ratio. What is the set of equivalent ratios? What's the proportion? That's the word I can't think of. What's the proportion that we can set up here? Who can volunteer to tell me? Obviously, we need to use K, because that's what we're trying to solve for. This should be review type stuff. That's why we're starting on this. Ellie? I saw the half hand.
3 or 1/3.
So you said what over what?
3 or 1/3.
How are you saying 3 or what? So I know what you're giving me, but how'd you get that?
Because so you can do, I think 4 over 12 and 3 over 9.
And you know that the 4 would correspond to the 12 or the 3 would correspond to the 9 because the order up here, right? So if we're using K, we got to use the 4.5 in the K. But yeah, you're right. There's a scale factor here of either 3 or 1/3. So absolutely. So what would we get for K? Who can tell me what that value comes out to be? Just shout it out. Yeah, 13.5. So I will go ahead and respect you guys enough. I don't think we need to write this down because we have plenty more to write down today. So in these triangles, just pay attention to the order given in the similarity statement. Sometimes they reflect or rotate in a weird way. So PQ here, 10.5, our top side relates to FG, right? So top to top. And then QR, well, QR is our bottom here, to GH, also our bottom. Be careful though. They like to flip triangles in weird ways. So the bottom might not be the bottom here. So just watch out for those. All right, so now we're working our way to the advanced stuff. What do I need to do here? Because I'm trying to remember how much we've already figured out or not. What do I need to do here to relate our variable and be able to set up the ratio to solve it? Actually, everyone go ahead and try this on your own, because this would be a good test. So write this one down. Write down the ratio we're going to use, and then go ahead and try to do the algebra to solve it out. So I should essentially either see you looking at the screen or the top of your head while you're writing. The tricky part here is that the variable is going to show up in 2 places, right, in this ratio that we set up. So I can actually probably zoom in on this a little bit. So our similarity ratio, if we go big to small, so big triangle over small triangle, I can put the 5 over the 1, right? So relating DE to BC. But when I go to set up the bases, the base of my larger triangle is the binomial 9 plus x. Base of my small triangle is just x. So then we're going to cross multiply and do the algebra from here. Does anybody have questions on how I set up my big triangle compared to my small triangle, which then my base of my big triangle is 9 plus x, base of my small triangle is x? Kaylin?
Question about that, but wouldn't x over x just equal 1? Like
You're
9 plus x over x, so you could just do both x's and get 1.
So you're saying this becomes 1?
Yeah.
Can't do that because the binomial with addition. So you're right, an x over an x would be 1, but because this is stuck together in the binomial with addition, this is really like one term. The x is trapped. Now, if we were multiplying, we could split the division by x, because remember, we're dividing by x, by being over x. So really good question here. And I remember in high school, like, falling into that trap of here I would have reduced and said, oh, it's just 9. Can't do it because the addition. If this was multiplication or division up here, then the rules would be different. Then we could split the fraction into 2 fractions, solve it that way. So when we cross multiply here, we're going to get 5x equals, well, that's easy because we're over 1, so 9 plus x. Do the algebra. Might as well just take this x away from both sides. So 4x equals 9, or x equals 9/4, or as a decimal that is 2.25. Any questions on how we solve for x there? And or Kaylin, really good question there, or why we can't reduce this out. The addition breaks it. Sorry, trying to get that to focus.
Is the first fraction b over 5?
Sorry, that's b over s because big over small. I just wanted to set up what I was setting up. Because you could also set up 1 over 5 equal to x over 9 plus x. You could set it up small over big. I find it easier to have the larger numbers on top and the binomial on top just for how to look at things. So I would always advise putting the larger triangle over the smaller triangle. And if you don't want to write BS on your paper, you could write L over S. After I wrote it, I realized, oh, you just wrote BS. All right, try one on your own then, because I really walked through that. I know this is like exactly the same. I know this is like exactly the same. That's why I'm checking. Can we all get the same answer? When you get your answer, drop it in the chat privately to me if you can remember. It's okay if you forget and put it to everyone. But when you get your value for x, drop it in the chat so I know we're ready to move on or if we need to go over this. There's a trap door here involving a distribution. Now, that couldn't have come out cleaner. Remember, when you get your answer, drop it in the chat what the value of x is. If you can remember to send it to me privately, that would be sweet. Yeah, I like how you guys are all leaving it in fraction form. There's a gnat in here from my plant behind me. Sorry, if I clap, it's because I'm trying to get the gnat. Aha! I got it. Have you guys ever seen Karate Kid? I'm just curious, like, how far back? Katie and C. Yeah, okay. Yeah. Oh, I have to send attendance. We're all here. Now, I do have one answer that seems slightly off, so I want to make sure we go over the process real quick. I decided to change it up and put my small triangle on top and my larger triangle on bottom here. So I put the 3 over the 11 and the x over the x plus 9 just to change things up a bit. When we distribute, and here's the trapdoor you may have fallen in, make sure that you got a 27 from applying the 3 to the x and the 3 to the 9. Because remember, this part of the cross multiplication is 3x plus 27. This side gets 11x. We subtract 3x from both sides and get 8x. So then we divide and we get that x is, as most of you left it, 27 over 8. We also had the answer of 3 3/8, which I think seems right. So be careful. I got one answer in there that's less than 1. Yeah, so let me know if this doesn't make sense, how we get to this. I think your goof might have been here. Because if that was just a 9, yeah, I'm betting that that is what happened. All right, unless we have questions, let's try this one, slightly different form here. When you get your answer, drop it in the chat. It really does help me know because I can try to identify what mistakes maybe happened by seeing what the wrong answer is. And obviously if it's a right answer, that's a really good thing. Hey Aaron, you are actually here, right? I'm only asking because your camera's off and you didn't. Okay, you didn't drop an answer in the chat, so I was just checking on you. You're good. I don't care that much about that. I just wanted to check in because you did not drop an answer in chat. I just wanted to check that you were here. You're good. You're good. So this one, in my opinion, might be slightly easier. That x is not split up through a binomial, right? Just be careful that when you're using the pieces of the base, that you don't just use one of the pieces, that you use the whole thing. Again, this is one of those cases where the fraction form is just more accurate, right? So don't try to put your answer as a decimal unless you need to. And none of you guys have. I am just a huge advocate for leave things as a fraction. Yeah, good work, guys. So just to review the work on this one, if you set up large over small, that would be 1 over x. Again, the x does not need to be in a binomial. This 3 is the trapdoor, because that actually comes from the 2 plus the 1 across the bases. That's where they're thinking that you might trip up. Try this one real quick. Should be like one proportion and then an answer, and then we're moving on to way more difficult things. I promise you, if this is leaving you hungry for more difficult math, you'll get it here in a second. If anybody has any questions, please send it to me in the chat so I know not to move on. Yeah, again, a really terrible value that we should just leave as a fraction. I don't have any last questions on this sort of work. All right, to review that real quick before we move on, if you put the larger triangle over the smaller triangle, we'd have 4 over x equivalent to 7 over 4. So guys, now when we move on, it's going to be harder to build these proportions, and we really have to double check that we build it correctly. And one of the ways that we can build proportions is by using other theorems. So if you haven't started the work from Khan Academy for this week yet, totally fine. But this is one of the things that we have to know moving forward. The angle bisector theorem is a way that we can split up one triangle into multiple triangles where we can use the ratios to solve for an unknown piece. So if a ray, we lost somebody. I'm probably going to have to repeat myself once Calvin gets back in here, so I'll just wait a second. Calvin, you good, dude? All right, glad to have you back. So I would maybe draw a picture of this in your notes if I was you. If a ray bisects the angle of a triangle, what's bisect mean? Somebody unmute and tell us. What's bisect mean? Oh, come on. I know we're all... Yeah, split in two. Split in two equivalent pieces, right?
Do you want us to write it or draw the picture?
Yes. Whatever you want to do so that you can remember it. So if you need to write it, that's fine, but I think just the picture and the proportion is the most important thing here. So we're splitting up the third side of our triangle because we're bisecting that angle there between A and B, but this works in any direction. Like, because triangles can be rotated, so as long as we can bisect the angle, those split pieces now become part of those proportions. Can anyone tell me what you notice about the proportion? Like, if we're going to relate and try to remember this, because, I mean, our goal is probably memorize this. I dislike trying to cut things in half. Stresses me out. So here's the notation we want to make sure that we have in our notes. When we draw this ray, even if we don't accurately bisect, by drawing this notation with the arcs that have the same amount of tick marks on them, that is what tells us that our angle is bisected, that both of those are equal to each other. So then make sure that we have A labeled on top, at least in this picture, B over here, and then C and D. And of course, you'll find models where it's like the points are labeled and then all of the lines are given to you in segment notation. This is just an easier way to build the ratio. So notice A is going to relate to C. And the original side A we put on top and we relate it to C. So that left side of that proportion is A related to C. The right side of the proportion, same thing. The original side of B related to the partial side now D. So A over C will be equivalent to B over D. And we can prove this, and we actually probably will prove this. But right now we're just, I am just sort of asking you to operate on believing me that this is true. This will always hold true, and we will prove it here very soon. So anytime you see theta notation, it's either being used to represent like an unknown angle, but if you have x equal to x, you know that the x's are the same, right? So theta being like a variable, if you have theta here and theta there, you know that these angles are actually equivalent to each other. So go ahead and try to set up the appropriate ratio here. And guys, if you don't have a calculator within your reach, get one, because you want to practice calculating this stuff. What is the length of AC, our unknown, our question mark here, when we apply the angle bisector theorem here? So go ahead and take a moment to try this. If you don't have a calculator, you need one. I swear I brought mine up. When you get your answer, just throw it in the chat, please. Again, it just really lets me get a good check mark of, are we understanding it on the get-go, or are we having some issues? Rounding to 2 decimal places is fine, by the way, when we're doing this calculator work. Remember, the ratio that we're going to set up is going to relate the original side to its corresponding partial side. So we could do 5.5 over 2.8, or vice versa. And then the original side, so our unknown here, to its corresponding partial side. Yeah, the answers that are coming in are correct. If you've already sent your answer, it is right. There we go. Thanks, man. Thank you for letting me know. So angle bisector theorem is written down in your notes, right? So the issue with us still being remote is I can't like hand you a printout that you can just draw on. But if you look at this triangle and do what we did in our notes, so I would draw a picture like this where you can see A relates to C because that's the corresponding side. The other thing you can tell yourself is the ray that is part of the angle here, then the angle kind of points at the opposite side, right? So when we think about angles, the size of the angle determines how big this side is going to be. And have we talked about the hinge theorem? Like hinge of a door? So the hinge theorem is a theorem that says the length of a door and the amount that it's open, so the size of the angle, will determine the space that has been opened, right? And it's a lot more formal than that. But like literally H-I-N-G-E, like hinge on a door, there's a theorem called the hinge theorem. And it's how we relate the ray, the leg of the triangle, the amount of the angle that is open, and then the space that it creates. It's based off the hinge, right? How big the angle is. So here we relate our A to C, quote unquote, which in this case is 5.5 to 2.8, right? If I just want two actual values that I have, 5.5 over 2.8, and then equivalent to the original piece of the triangle to the partial piece, right? So question mark over 3. Do you have questions on how I set up this proportion?
No.
Okay, so then we cross multiply, right? We get 16.5 from this cross multiplication. 2.8, I went ahead and set X instead of a question mark because I don't like writing with question marks. I should probably make my decimal a bit bigger there, easier to see. And then we do the division on both sides. Sorry that my 8 looks funky, but we get 5.89. Remaining questions on that one, Amar?
I didn't get it.
Let's verify if you get it. Let's try another one. Guys, sort of try to envision the proportion that you're going to make. Like draw your ratio line between the original side and the unknown. So I'm going to start writing this one with 4.3 on the top left of my proportion. Because when I look at this picture, that's easier for me. That was quick. By the way, I want to take back an earlier statement. If you want to get in the habit of 3 decimal places, it's all the answers in the chat are fine. But 3 decimal places lets you have the extra accuracy beyond currency. So we normally round to 2 decimal places in currency, right? If you want to get in the habit of 3 decimal places, that's not a bad habit to get in. Okay, 1 decimal place, that's not acceptable. So if you just sent me a 1 decimal place answer, first off, we don't round to 1 decimal place. Second off, you rounded that incorrectly. So be careful. If you just sent me 5.4, this would not even be 5.4 unless your answer is actually wrong, because this is 5.483. That would round up to 5.5. Right? If we were going to round off to 1 decimal place, it would be 5.5. But we don't want to round off to 1 decimal place. We might as well go 3 decimal places. Any questions on that one? Oh, this is about to get so fun. What about this? This one's different. I'm going to let you figure out how it's different. But this is the last one of these we're going to do unless anyone says they have a question. Try this one. It is different. Not by much, but it's different. Anyone want to tell me why this one is different? It's not any more difficult. It's just a tiny bit different. The unknown ends up in the top of the variable here. Right, which I guess it did on the problem 2 ago. Yeah, all of these keep being like 5. Right? I don't know, kind of like your brain is like, why are these all 5 something? Like, I don't know if you guys like recognize patterns that probably don't exist, but my brain right now is like, why are these all 5? 5.413 repeating. If we want to be particular enough to put the repetend, I don't know how you would type that in the Zoom chat, so please don't ask me. But yeah, 5.413 repeating if we wanted to be particular. Alright, so now let's step it up a notch. You guys are acting like you're big, bad, tough mathematicians, and you're making things look easy. We can't have that. So, check it out. First off, yes, if you recognize the 5 and the 12 here, who, shout it out, unmute and tell me what your brain might be like. Ah, this is a special right triangle. I don't know if you've learned this yet. Nobody? Nobody? 5, 12, 13. Does that ring any bells? Come on, Alina. 5, 12, 13.
Do you have like a specific angle to all of them?
So, in right triangles, there are certain right triangles that we call special right triangles. You know, like us Phoenix people are special people. But our special right triangles have certain properties.
Is it the 90 triangle?
So, this is a right triangle, and we know that there's a few reasons. One of them is because when the legs are 5 and 12, and the hypotenuse is 13, that has to be a right triangle. This is just one of those special right triangle theorems. But check out what we're going to do with this. This is an application of the angle bisector theorem. And I actually, to save class time, I would like you guys to go watch the Khan Academy video on the angle bisector theorem. But I didn't assign it, and here's why. I want you to be able to skip through the video and replay it as you want to. But this is an application of the angle bisector theorem, because what we actually do to apply the angle bisector theorem, if I come back up here, and you don't have to draw this in your notes. This would be really complicated for you guys to draw, which is why I've structured class like this today. If we draw a line parallel to what we've called line B out here, maybe something like that. And if we draw a line parallel to line A and connect it down to this vertex, what have we created? Parallel, parallel. Yeah, you guys can just shout it out if you want to. You don't have to type everything in the chat. We create a parallelogram. Right? And we can do this in different ways. So instead of us spending 15 minutes on Zoom trying to do a proof that I'd rather you have, like, Sal Khan explain to you, the angle bisector theorem comes from a proof that we can build using parallelograms. all of that to say I only have 10 minutes left and I want to cover a lot more content, so that's why we're not going over every detail there. But if we did that, if we created a parallelogram here, which looks a lot like a rectangle in this situation, we would know that angle BRO would be equal to angle ROA, because they're alternate interior angles, right? Do you remember our parallel lines theorems? So parallelograms involve those parallel line theorems, right? This is where everything comes back together and you're like, gosh, there's so many layers. It's like a really good cake, right? So these alternate interior angles would be congruent to each other. We could drop in altitude and create a right triangle right here, right? From there, we can solve Pythagorean theorem, do whatever we want. But what we can also do is set up similar triangle ratios. So relating triangle PAO to triangle BOR, we're allowed to set up new ratios, and this gets into like a whole nother layer of theorems that we're going to start to apply. So take a second. I wish this was better color coded. Sorry, I was cutting pictures out of something and I couldn't figure out like exactly how to layer things on. But here's PA, right, related to BO, OA, RO. What are they relating? The longest leg to the hypotenuses, right? So in right triangles, we always have short leg, long leg, hypotenuses. So short leg to short leg, long leg to long leg, hypotenuse to hypotenuse. We can build any proportions we want as long as we keep those equivalent to each other. Now, another theorem we don't have time to get into today is that anytime we draw right triangles inside of each other like this, when we drop an altitude from one point, because remember, an altitude hits at 90 degrees, and drop does not have to mean down. Drop just means like draw, right? So if we drop an altitude from A to P, we create a similar right triangle. That's another theorem that we'll continue to get into. I just want to try to get you guys ready for all the next practices. Then we'll come back and we'll talk more about this, okay? Take a moment here. What is even going on? What could we do to visualize how we could relate triangles in this diagram to each other? It wants us to find the area of triangle DUO. So we need to know that height, or that altitude, right? What could we do? Amar, because you went ahead and turned your camera off, I'm going to call on you. Do you have any ideas here?
I don't know anything to do.
Oh, you know a lot of things. Margaret, any ideas? Alina, I see you. I'm just calling on people with cameras off. I want to put you guys into 3 breakout rooms to chat ideas really quickly, but here's the problem. When you go into the breakout room, you won't be able to see this unless you have Schoology open. We have 5 to 10 minutes left. I want to throw you in the breakout room just for like 2 minutes and see if anybody is bold enough to share an idea when you're not in the call with me. All right, go real quick and chat. If you have Schoology open, you'll still be able to see this.
said to leave the breakout room.
Yeah, it gives you guys 1 minute to do so.
Oh.
I wish I could set it to just give you a countdown and bring everyone back at the exact same time, but it likes to give flexibility, like in case you guys were deep in conversation or something. But I wish it could just be like, all right, 1 minute left. Like Amar, Ellie, and Katie Ann must be deep in a conversation because they're not leaving. They're just going to let it like bring them back. Or they all took a break. There, everyone will come back. Anyone have an idea? What do we think? I'm still screen sharing, yeah? I wanted to make sure the breakout room didn't break that. These angles are congruent to each other, right? Did we all notice that? What does that then mean? If these angles are congruent to each other, what else does that mean? Alina?
I think it means that MDU is congruent to
Sorry.
PDA.
Yeah! Guys, based off the shared relationship of these congruent angles, their complements, remember the angle pair with a right angle? The complements will also be congruent because, look at this, DR is perpendicular to OP. We know that there's a right angle over here and there's a right angle over here. So based off of that, this angle here, PDA, is equal to angle MDU. So what we can actually set up is that this 3.75, the base of that triangle, 3.75, and this is a problem you might see in your homework, by the way. So the base in the smaller triangle, and we're just calling it base because it's got the right angle on it, right? A lot of times we like to call this the base and this the height or something like that. The base of 3.75, what could we relate that to? Would it relate to 10 or 4? Right? I may have moved too quick here. Let's circle back. We know that angle DMU is similar to angle DPA through angle-angle similarity. Because we see that there's a right angle at point M and a right angle at point P, and these angles, I'm going to skip their names, but these angles right in here are congruent to each other at point D because of the shared congruent angles on the outside. So because they're complementary, we get an angle-angle similarity. So if you need to write down first, we can see angle-angle similarity. And that's how we set up 3.75 over 10 is we're relating base to base. But if we're relating base to base, then we could relate height of 4.5 of my smaller triangle to the line segment. I'm going to say MU because UM is gross. Sorry, UM, University of Michigan. Sorry, it's a bad joke on Michigan. So, small triangle to larger triangle, bases. Small triangle to larger triangle, heights. Guys, this is probably one of the most complicated parts of your homework, of the work that I've assigned, is being able to recognize that these triangles are similar to each other and that I can set up the proportion like this. I'm not worried about you guys doing the algebra, solving the proportion, doing the cross multiplication. That's easy compared to figuring out what is similar to what. So take a moment right here. What would be the proportion that we could build here? If we're asked to find BD, sorry, you can't see it because it's covered up right now, but if you're asked to find the length of BD, and we're going to start using segment notation here, right? So set up the ratio, or sorry, the proportion, ratio equal to ratio, set up the proportion that we can use here. So we see these shared congruent angles mean that their complements are congruent, meaning we have angle-angle triangle similarity. Go ahead and solve. We'll use this as the final problem for today. Go ahead and try to solve. I know that you need to get QD before you get BD, so go ahead and try to solve for QD. If you have a calculator, it should not take too long. So we're now using segment notation. This is one of the proportions that you could build. You could have built it a lot of different ways, as long as you're relating those corresponding sides to each other. So we get that QD is 9. Yeah, yep. Good work, L. Good work, Alina. Meaning that BD would be a total of 24. So if you see this on your homework, there's a freebie for you. BD would end up being 24 because QD is 9. In a situation like this, we can see similar triangles because I'm not going to solve this for you. I just want to make sure that you recognize some of the problems that you're going to see. What do we see right here in the middle? What sort of angle relationship? Shout it out when we have angles across from each other. Ooh, close. Starts with a V. Vertical. We don't know that these are perpendicular. We actually don't know that. What we do know is they're vertical angles. And then, guys, always look for parallel. We have sets of parallel lines, meaning that alternate interior angles will also be congruent. So angle H would be congruent to angle D, right? Those inside angles. H would be congruent to D. We can prove these triangles similar based off angle-angle. Here, we're going to use that right triangle proof that we talked about. If you get confused as you're working through your work in Con, please use their help tools. Like I said, we don't have enough time today to really talk in depth about everything. But notice from the right angle, we drop in altitude to make a new right angle. This is going to create similar triangles. Please use the help tools if you've never seen this proof before and if you want to see it walked through. And that's everything I was trying to get through today. So stick around if you have any questions that you need to ask me. Aside from that, thank you guys all for coming and your attention. And I can't wait to see you in school next week. So have a great day. Bye, guys.